In this section, we're going to talk about how to calculate heat during changes of state. So changes of state of matter, of course, on our heating curve are on the flat line parts of the curve. So this part here is melting. This is the transition from solid state to the liquid state. Then we have, after the liquid increases in temperature, when we get to this part of the graph here, that is, of course, vaporization. That's when we're transferring from the liquid state to the gas state. So when we're calculating heat during these changes of state, we need to use what's called the molar heat of fusion. This is the heat absorbed by 1 mole of a substance in melting from a solid to a liquid. So the formula for heat of fusion, or that we'll use when we're using heat of fusion, is Q equals mass times the heat of fusion. If we are vaporizing, if we're on the second flat line part of our heating curve, we have the molar heat of vaporization. This is the amount of heat necessary to vaporize 1 mole of a given substance. And the formula is very similar, Q equals M, but this time we're multiplying by the molar heat of vaporization. So the heat of fusion and vaporization in water are given to you on table B. So table B only has 3 numbers on it, and they are almost exclusive. Oh, I'm pretty sure, yeah, they're pretty exclusive for this chapter and the calculations that we'll be using in this chapter. So you don't need to memorize these numbers. You just need to know to go to table B to look up for them. And remember, this is only for water. If the question is about some other substance other than water, they have to give you these numbers somehow in the problem. Okay, so let's look at our formulas that we've learned in this chapter. There's 3 of them, and they're all on table T in the little section on heat. So the first one is Q equals MC delta T. I usually call this equation number 1. And then we have the 2 new ones we just learned in this section. Q equals mass times heat of fusion, and Q equals mass times heat of vaporization. So the challenge here in this chapter is knowing when to use which equation. They're all given for you, and they're not complicated equations. But what kids usually struggle with is picking the right one at the right time. Okay, so here's how you decide. We need to figure out in the word equation where we are on the heating curve. Now, the question is probably not going to give you a heating curve, but you need to be able to either visualize this in your head or sketch it out when you are analyzing the question you're trying to answer. So each section of this graph is called a leg. So this is leg A. So this change here. Which formula would we use if we were trying to solve for the enthalpy that is going on in leg A here? Well, we would actually use equation number 1. And the reason is because we have a delta T. We have a change in temperature. During the course of leg A, we're starting at one temperature and we're ending at another temperature. So if you have 2 different temperatures in the problem, in the word problem, you know it automatically has to be equation number 1 because the other equations don't have delta T involved. So on leg B here, we would use the heat of fusion formula. So the reason it's fusion is because we are melting. We're going from a solid to a liquid. And also we would use this for freezing. So heat of fusion works for melting, going up the curve, or freezing, going from a liquid down the curve to a solid. Heat of fusion is the same. It just matters if we're adding that much energy to the water to melt it or taking away that much energy from the water to freeze it. Okay, on leg C, the 3rd section of our graph here, again, we have a delta T. We have 2 different temperatures, so we would use equation 1 once again. On leg D, we are now going to be using the heat of vaporization formula because we are going from a liquid to a gas going up the curve. So that's heat of vaporization. We would also use this formula for condensation, going from a gas down to a liquid, because again, it just depends on whether we're adding that amount of energy to vaporize it or taking away that amount of energy to condense it. In leg E, again, we would use equation number 1 because we have a delta T. We have a certain temperature we're starting with and a certain temperature we're ending with. You can subtract those, and there's your delta T. Okay, so let's look at some example problems. How much heat is needed to completely change 10 grams of ice to water at the melting point temperature? So which equation would we use to answer this one? 1, 2, or 3? So let's look at where we are on the graph. So I have 10 grams of ice and I am turning it to water at the melting point temperature. So where on this graph does melting happen? Well, that of course is right here. So that is the heat of fusion. So I would use the heat of fusion formula. So they're asking for the heat. So I'm solving for Q, the amount of heat needed to change 10 grams. So I'll plug that in. To ice. So what do I use for heat of fusion? A lot of kids will get stuck here, but if you realize that we're talking about water, that the heat of fusion is on table B. So you go to table B, look up the heat of fusion of water, and it is 334 joules per gram. Okay, so if we look at our units here, we see that I have grams on top, and I really have grams below here. So these two are going to cancel and leave me with joules, which is a unit of heat, so I know I set this up correctly, and 10 times 334 is 3,334 joules. Next question says, how many joules of energy are required to vaporize 423 grams of water at 100 degrees Celsius in 1 atmosphere of pressure? Okay, so let's visualize where we are on this graph again. So we want to know how many joules are needed to vaporize this much water. So where does vaporization happen? That's a change in state. So that's on the flat line part. I'm taking this liquid water and vaporizing it or boiling it into this gas. So right here, of course, that is the heat of vaporization. So I'm going to use equation number 3. So Q equals mass times the heat of vaporization, or mass is right out of the problem, 423 grams. The heat of vaporization for water is, of course, right off of table B. That's 2,260 joules per gram. Joules and joules will cancel, and if you multiply those two numbers together, you get 955,980 joules. Okay, so when calculating heat during a change in a state of matter, use either the heat of fusion formula or the heat of vaporization formula. If we're calculating heat not during a change of state, we're going to use Q equals mc delta T. So the heat of fusion formula is just mass times heat of fusion. We're going to use that whenever we're talking about melting or freezing. Again, it just depends on whether we're adding enough energy, the heat of fusion, to melt it, or taking away the energy or the heat of fusion to freeze it. And the heat of vaporization formula is Q equals M times the heat of vaporization. And we'll use that for boiling or vaporization, going up the curve, or condensation if we're going down the curve. And if the question is about water, the physical constant values that you need are on table B. If not, they have to give you the values in the problem somewhere. Okay, one other thing I want to say before we wrap up here is don't be afraid of really large answers. If you remember the last two problems we did, they were like 3,000 and 955,000. Sometimes kids will get these answers and stop and say, well, that can't be right. My answers aren't usually that big. But when we're dealing about heat changes, especially like in changes in state and matter, it's actually a really large amount of energy, especially in water. So don't be afraid of large numbers. Pick the right formula, sketch out heating curves, and decide where you are on the heating curve to pick your right formula, and solve for heat. And that's how we do that. So if you have any questions on this or anything else, please let me know.